Nutations. Generally speaking, the angle theta between the principal axis E3 and space axis unit vector z hat will not be a constant. Instead, theta will perform bounded periodic motion, which looks like nodding. The word nutation comes from Latin that means just that, nodding, periodic nodding. We want to figure out the solution for theta, which we can do using the result from previous lecture, where we found the Lagrangian, and we can write the equations of motion and solve the second-order differential equation for theta. Alternatively, we can proceed by writing energy conservation. We found the expression for kinetic energy last time for a symmetric top to be given by half lambda 1 phi dot squared sine theta squared plus theta dot squared plus half of lambda 3 psi dot plus phi dot cosine theta all of it squared. And for potential energy, it will be equal to total mass m, g, gravity, r, position to the center of mass, cosine theta. We also found last time that generalized momentum p phi, which we found to be lambda 1 phi dot sine squared theta plus lambda 3 psi dot plus phi dot cosine theta times cosine theta to be constant, which we were able to identify as the z component of the angular momentum relative to the space frame. Also, generalized momentum p psi, which we found to be lambda 3 times psi dot plus phi dot cosine theta, is also a constant, which we identified as the component of the angular momentum relative to the principal axis E3. Let's use this knowledge about preserved momenta components to simplify how energy conservation looks like. In particular, from the first expression, from Lz being constant, we can write that phi dot to be, so note here that this expression is nothing other than L3, it's the same as this, and so we can write phi dot to be Lz, this is the right hand side here, minus L3 cosine theta, that's this guy right here, divided by lambda 1 sine theta squared. Also, we know that this parenthesis here is nothing other than omega 3, which is also a constant, which of course is L3 divided by lambda 3. We will use this expression to find the last term in the kinetic energy, because this is nothing other than omega 3 squared, as you can see. By combining all of this, we get that the full energy can be written in terms of, from the first term of kinetic energy, we have half of lambda 1 times theta dot squared plus, and here we substitute phi dot to find Lz minus L3 cosine theta, all of it squared, divided by 2 lambda 1 sine squared theta, plus, and the second term of the kinetic energy becomes L3 squared divided by 2 lambda 3. And we need to remember potential energy due to gravity, mgr cosine theta. Surprisingly enough, we can rewrite full energy in terms of the term that looks like kinetic motion with respect to theta, plus an effective potential that depends on theta. This effective potential is all of this here. So once again, we get a one-dimensional motion of theta in its effective potential. If you are to plot the effective potential, you will discover that it looks as following. Theta changes from 0 to pi, and the effective potential will look like a bathtub curve, something like this. Full energy, E, let's say it's given by this line. So we get a bound motion from theta 1 to theta 2. The nature of this motion will be that theta oscillates periodically between these two values, theta 1 and theta 2. Which is precisely what nutation is.